Okay, so we finished off talking about predictions. So I'm just actually going to plot some of those predictions in ggplot. So what we do is, remember we finished off, we just were doing the predictions. So we use the predict function, we use the data frame, we tell it we want a prediction interval at 95%, and then we use cbind to add it to the data. So let's do this. We can look at our data, and we can see that we have the original data, but now we have the actual predicted value for each of the movies, and we have the lower bound and we have the upper bound. And then we can run one of my fancy ggplots. All that's saying is we do ggplot AES with the tweet rate per hour and the revenue per million. So we're actually just creating a scatter plot here with the tweet rate per hour on the X and the revenue per million on the Y. And G on point is like the ggplot scatter plot. But we also use stat smooth. Now what this does is this creates a 95% confidence interval, and it shades it in grey. So we've got, and it also kind of plots the regression line here. So, and then we can add our own manual little lines, which are geom line, which is a lower prediction interval, and the upper prediction interval, which we colour in red. Then we add the labels for the X and Y axis, the title. This is just putting the title in the center, and panel background element blank, just making sure we have a nice white background. We don't have like a checkered background or anything. So let's just put this all together, and you can see I actually just ran it before just to check it. And you can see actually, most of the data is pretty much in this first half here. And as we get further and further along, we actually get wider and wider confidence intervals and maybe a slightly wider prediction intervals. Okay, so we've made predictions. What else can we tell from the regression? Well, we can actually do some statistics to see if our regressions are significant. So if you recall, and you can go back to the last video if you can't remember, but I had the sum of squared total equals, this is the total amount of variance. So this is total variance. Equals the sum of squares regression plus the sum of squares error. So I'll just say SS regression. And remember, I kind of showed this visually on my little tweet rate example. So we can actually put this into a table. And if you recall from your business stats, this is going to be called an ANOVA table, where we're just decomposing the variation. So this is the DF, degrees of freedom. And this is the sum of squares. And this is all in the notes. And this is the mean squares. And then we have the F statistic. I think I can just about do it here. And this wonderfully symmetric and straight table. Okay, so we have the regression and the error add up to the total. And so we can put in the sum of squares. We have the sum of squares regression, sum of squares error, and sum of squares total. Now sometimes these, depending on which book it is, sometimes these guys are flipped around. Now the degrees of freedom, this is just, you have one for every data point. Total, we minus one because we're calculating the overall mean. Remember the total, we subtracted everything from the overall mean. The regression has k degrees of freedom. And the error is basically whatever's remaining. So it's n minus k plus 1. Add these two guys together and you get n minus 1. And I've already told you adding the R regression to the error is the total. Now, the mean squared is just the sum of squares divided by degrees of freedom. As I said, this is bringing you happy memories of, if you were at Mississippi State, of your business stats too. So this is the sum of squared regression divided by k, and the mean squared error is the sum of squared error divided by, and we're a little bit small here, but that's just divided by n minus k plus 1. And then the f is the mean squared regression all over the mean squared error. What does this mean? Well, it means basically the higher the f, the more significant. So if we had, this diagram, and we have like a really strong line, and everything's really close to the line, then that's going to be a high F. But if we have, say, kind of no real line, then, and we got a big error, then this is going to be a low F. You get that going back to what I said previously, the regression is the difference between the points and the mean. The error is between the points and the line. So this ratio, this would give us a high F and this would give us a low F. And there's also a little statistical test we could do. Let's just move that up a little bit. And this is a test for the overall regression. So we have the statistical test. And the null hypothesis is that all my betas are 0. So all these regression coefficients I showed you before are equal to 0. And the alternative is at least 1 beta I is not equal to 0. So this is just saying, hey, the regression is useful. So this is telling me there's something useful in the regression. And my test statistic is F, which is the mean squared error, mean squared regression all over the mean squared error. And we're going to rejection region. We're going to reject H0 if F is greater than F alpha, and we have 2 degrees of freedom, which we actually take from the ANOVA table, which I've just hidden. So V1 is the numerator degrees of freedom. So that's is K. And we also have the degrees of freedom here, which is N minus K plus 1. So V1 is K, V2 equals N minus K plus 1. Now, of course, if you're doing business stats, you would kind of look it up, and it looks a little bit like this. It's almost like a little bit like the chi-squared, but even more skewed. So this is my F alpha. So my F gets bigger and bigger and bigger and bigger. We get more to the scenario where we have a kind of a quite a slope on the line and very little error. So my F gets bigger and bigger and bigger and bigger and bigger until we actually reject. So this is reject. Now, the area to the right of whatever my F is, this is going to be, in blue, is the p-value. And that there to the right is alpha. So we're also going to reject if the p-value is less than or equal to the alpha. Okay. Now let's kind of go back to this table here. And we have something else that we're interested in. The r squared, let's get back to my black pen. The r squared is the sum squared of the regression all over the sum squared of the total. And you can also write it as 1 minus, just a little bit of algebra, sum squared error all over sum squared total. And this is the proportion of variation in the data and in particular in y accounted for by the regression model. So if every single item kind of was on this regression line, then the error would be 0 and you get a value of 1. If we had pretty much as much error as we did of like total sum of squares, then the r squared would be 0. So basically, it's just a measure of how good the fit is, in addition to the statistical diff. This is almost what we call an effect size. So, if you have you had millions of records, you may get a statistical, it may be statistically significant, but this guy might still be quite small. So generally, we look at both. We look at both. Is it significant? And, how big is the r squared? And then the final thing is as k increases, we can add kind of more and more junk to the model. So more and more, we went that example where we got to the 20th variable on my prediction model for movies, and it was what the actors had for lunch. That's not actually going to make the r squared any worse, because you could just set the beta for that x to be 0. But it is what we call, we could overfit the model. We basically have too many variables. So we want an r squared that accounts for the number of kind of predictive variables. And this is called the r squared adjustive. And this is just, you can actually work, I won't do this now as the videos are quite long this week. But it's just as k kind of gets bigger, it makes the r squared smaller. You can kind of play around with this and put it into a spreadsheet. So as k gets bigger, so k increases, then r squared adjusted will kind of decrease. You can see that this kind of number gets bigger and this gets smaller. So it just kind of weights things a little bit differently. Okay. So we have one more little statistical test. Now, so I go to my boss and I say, okay, I've proved my regression is, that predicts movie revenue is a really good regression. I know at least one of my predictors is useful. And my boss goes, well, you're an idiot. You haven't told me which is useful. So this is why we do another test, which is just predicting the individual variables. So we can also test individual variables. And this is actually going to be a t-test. And so what we're going to do is, are the individual beta i's significant? And this is a t-test, and it's the same as the other t-tests you've done. So you can do a two-tailed test. And my null hypothesis is that beta I equals 0. And my alternative hypothesis is that beta I is not equal to 0. And we can have a one-tailed and that would be beta I is still equal to 0. HA beta I is either less than 0 or BI is greater than 0. One of these guys. Okay, now the test statistic. The T is just really a scaled version of beta I. It's scaled by its error variance. And to work out the error variance, you kind of need matrix algebra. So we're just going to kind of ignore this for the class. If you want kind of more theory on this, go and see, the ISLR textbook, which will give you a little bit more theory on that. And so the idea is, we've got our regression coefficient. And if the beta I, we assume beta I was 0, and if that's true, then the t is 0. And as our beta I gets bigger and bigger and bigger, our t gets bigger. As it gets smaller and smaller and smaller, our t gets smaller. And for a two-tail, it's exactly the same. We're going to reject H0. It's exactly the same as the stuff we did in chapter 2. If the absolute value of t is greater than t alpha over 2. The only thing is the degrees of freedom is going to be n minus k plus 1. As we calculate more parameters, we lose degrees of freedom. So it's exactly the same as the t-test you did before, but we have different degrees of freedom. And again, the one-tailed, we're going to reject H0 if t is less than minus t alpha, or for the second instance, if t is greater than t alpha. So again, we have these, say we have a one sample, we have alpha over here, and our t, we kind of basically reject when we get past the t alpha. Now, interestingly enough, the p-values are exactly the same as the standard t-test. So let's go back to the two-tailed this time. And so we have our alpha over 2, alpha over 2. And imagine we had a t here. This would be the p-value over 2. This would be the p-value over 2. Or here, we had a t. This would be the p-value. And we also reject H0 if p is less than alpha. And again, this is why in some instances this class is harder than business stats. In other instances it's easier, because when we do the computational techniques, we're pretty much just going to reject if p is less than alpha. And it's going to be the same every time.